Far from the bright centre, the sky settles into broad structure that does not announce itself by starlight, but by the slow arrangement of matter on the larger scales. The cosmic web extends like a sparse net, with long filaments stretching between wide, low-density basins. These filaments carry galaxies' gas and dark matter toward places where many paths meet. One of those meeting places is the Phoenix Cluster. From this distance, the cluster is not yet a shape with edges. It is a node in the web, a quiet convergence where gravity gathers material drawn along threads that cross much of the observable sky. The web's strands are not solid. They are thin rivers of matter, most of it dark and unseen, some of it ordinary gas that remains too diffuse to shine on its own. Galaxies ride inside these rivers the way small boats ride a slow current. Along the filaments, their speeds align and their motions guide the flow toward the node. The space between strands opens into wide voids where galaxies are few and the gas is thinner still. The pattern is simple and persistent, empty regions, slender bridges and dense crossings. The Phoenix Cluster forms where several of those bridges arrive together. The structure rests on the long work of gravity. Tiny differences in density present soon after the first light of the universe grow over time, with matter drifting from less dense regions into more dense regions. Dark matter, which feels only gravity and not light, provides most of the pull and sets the scaffolding first. Ordinary gas follows the same pull. In filaments, the gas is warm to hot, stretched along the bridges, like faint mist in a valley before sunrise. It moves inward on long, slow paths, guided less by any single galaxy than by the combined shape of the surrounding mass. The scale is large. Filaments run for many millions of light years. Their cross-sections are measured in a smaller but still expansive fraction of that distance. The node at their intersection contains many galaxies and a deep well of gravity. From the outer web, the Phoenix Cluster is first a geometry, several strands that narrow toward a centre, where their directions align and their motions change. The light that marks this geometry is indirect. Galaxies within the filaments supply small beacons along each route. Their redshifts place them at similar distances and show a tendency to fall together toward the same destination. The faint glow of background radiation is gently distorted by the mass that sits in the node, bending passing light by small angles that reveal where the deepest part of the well lies. Maps that combine these signs draw lines through the outer region and connect them to the same point, a cluster growing at a junction of the web. The gas within the filaments is not uniform. Temperatures vary with depth in the potential wells that run along each strand. Densities rise slowly toward the node. Chemical traces appear where galaxies have over long times released heavy elements into their surroundings through winds and gentle outflows. Those elements mix into the thin medium and ride inward as quiet markers. Magnetic fields thread the gas and follow the same paths, weak in strength but persistent in direction. None of these features are strong enough at this radius to set sharp boundaries. They act as guides, not walls. The motion toward the node is orderly at this scale. Galaxies drift with the web. Gas slides in the same direction. The pattern on the sky looks simple, because many individual paths share a single broad gradient toward the cluster's centre of mass. The sense is of a basin fed by rivers. Each river narrows, the current grows steadier, and the water level rises where they meet. The web is not static. As matter flows along filaments, the filaments themselves gain contrast and the node deepens. The Phoenix Cluster sits in a region where several such flows are strong, giving it a surrounding field that continues to supply material across very long times. The outermost part of this field does not yet show the hot, bright atmosphere often associated with clusters. Instead, the medium remains thin and only moderately warm, its properties set by gentle heating, from structure growth, and by the faint background of radiation that fills space. The galaxies that inhabit these outer strands show a mix of types. Some hold steady disks with ongoing star formation. Others are more spheroidal and quiet, their gas already thinned by earlier passages through denser environments upstream. Their alignment along the strands is not precise, but their distribution shows the same tendency to point toward the node. The further one travels along a filament, the more these systems share velocities that carry them inward together. From this vantage, the Phoenix cluster's presence is a change in the web's pattern, rather than a visible object. The number of galaxies per unit sky area begins to rise along preferred directions. Background light is bent a little more. The temperatures inferred from faint diffuse emission creep upward, but stay far below the levels found inside a fully developed cluster atmosphere. The gradients are broad. There is time for matter to follow them without turbulence or abrupt change. The outer web also sets the eventual balance inside. The rate at which gas and galaxies arrive along filaments conditions how the node grows and how the central environment will later behave. Where inflow is steady and multi-directional, the node gains mass smoothly, and its outer shapes remain simple. Where one filament dominates the node can begin to elongate along that preferred axis. Around the Phoenix cluster, the web indicates several comparable strands, and their combined pull makes a nearly symmetric draw toward the middle, when averaged across large angles. The view holds on these outer distances and does not move inward. The aim is to let the eye rest on the layout before entering. The filaments can be traced by cataloguing galaxies that share similar distances and lie in long, thin associations on the sky. Weak gravitational lensing measurements fill the spaces between those bright points with a map of the mass that creates their paths. The intergalactic gas hints at its presence through faint emissions and absorptions that spread over large areas rather than clustering at a single point. Together, these signs describe an approach to the node that is smooth and continuous. Energetic events that will later shape the inner regions leave little mark here. At this scale, forces average out and motion owes more to the total mass distribution than to local disturbances. The quiet of the outer web is important. It allows slow settling and ensures that the matter arriving at the node has coherent direction. It defines the set of directions from which the centre continues to be supplied. It reflects conditions that prevail across most of the universe's volume, where structure is present, but not yet concentrated enough to produce strong shocks or bright emission. The Phoenix cluster seen here is a destination that the web makes visible by the way it bends paths and by the way it gathers. The surroundings do not terminate at a circular edge. They narrow and strengthen, guiding both galaxies and gas toward the same region of space. The sky around the node carries the faint signatures of this narrowing alignments of galaxy positions, gentle gradients in number density, and small coherent distortions of background light. The pattern sits against a quiet background of voids that separate one set of strands from another. The motion within the filaments continues. Over long intervals, the same roads deliver new material toward the same focus. At these radii, the properties of the inflow change slowly with distance and show no sudden transitions. The outer web holds its shape with only gradual variation and remains the wide frame that contains every interior process. The Phoenix cluster sits at its centre as a deepening intersection shaped from without by the calm, persistent draw of gravity along converging bridges. The view pauses here at the edge of the cosmic web that feeds the node with directions, traced motions aligned, and the broad structure set. The cluster takes on a clearer form as a single deep well that holds its contents in place. This well is the dark matter halo, a vast unseen mass that sets the gravity field for everything within the Phoenix cluster. Dark matter does not emit or absorb light. It reveals itself by how it pulls. Galaxies fall on paths shaped by this pull. Thin gas that spans the cluster sits in hydrostatic balance against it, with pressure supporting the gas against the inward force. Background galaxies appear slightly stretched where their light passes near the cluster, a gentle arc and shear called gravitational lensing that marks the distribution of mass in projection. These three lines of evidence, motions, gas pressure and lensing, agree that most of the cluster's mass is dark and spread through a large volume, with a density that rises toward the centre and falls outward in a regular way. The halo extends for several million light-years and encloses a mass that would be counted in many quadrillions of times the mass of the Sun. Its shape is not perfectly round. Statistical studies of many clusters find that such halos are often triaxial, more like rounded ellipsoids than spheres, and the Phoenix cluster follows the same expectation when its lensing map is compared with the distribution of member galaxies and with the pattern of X-ray brightness from hot gas. The outer slope of the mass profile is steep enough that the cluster has a natural boundary, where the mean density inside drops to a few hundred times the average density of the universe. Inside this boundary, material stays bound for long times, while outside the web still feeds the well. The regular rise and fall of density with radius is one of the simplest statements the halo makes, and it is the statement from which most other properties of the cluster follow. The measurement of this profile is careful and redundant. Lensing, which needs no assumption about the state of the gas, traces the total projected mass directly through the way light is bent. Where strong lensing occurs, multiple images and thick arcs appear and fix mass in the inner regions. Where lensing is weak, subtle alignments of many background galaxies reveal broader gradients. The motions of cluster galaxies supply a separate measure. Their velocities along the line of sight gathered into a distribution widen, where the gravitational pull is deep and narrow farther out. These velocities, with a model for how galaxies are distributed in orbit, families yield a dynamical mass that matches the lensing result to within known uncertainties. The X-ray emitting gas adds a third measure by writing its own pressure and density as brightness and temperature. If the gas is close to balance between pressure gradients and gravity, a relation between its profiles and the mass profile follows. When applied with care and with allowance for small non-thermal pressures from turbulence or bulk flows, this method reaches similar masses and shapes. The agreement among all three is the best reassurance that the halo picture is correct at the scale of the whole cluster. The halo does not keep a single temperature or a single pressure in the gas it binds. Instead, pressure rises toward the centre and declines outward in a way that can be described by a simple curve, while the specific entropy, which tracks the balance of heat and density, rises outward and sets how easily gas can sink. These thermodynamic trends are not properties of the dark matter itself, but are the imprint of gravity on the gas that lives in the same well, and they are easiest to understand once the well is established. Because the halo dominates the mass stars, dust and cold gas in individual galaxies contribute only small corrections at cluster radii. The brightest cluster galaxy adds light to the centre, and local gravity on very small scales, but its share of the total mass within hundreds of thousands of light years is small, so the broad shape of the potential remains that of the halo. A lesser-known detail sits in how the halo's assembly history can be read in the smoothness of its mass map. When a cluster has grown mainly by many small additions with no recent major merger of equals, its lensing map is calmer, its galaxy distribution more centrally concentrated, and its outer isophotes in X-rays show gentle symmetry. The Phoenix cluster shows a high central mass concentration for its distance, and a relatively regular outer appearance traits that point to a long period of steady growth along several filaments, rather than a single recent disruptive event. This is consistent with the presence of a well-defined boundary and a stable pattern of pressure with radius. Uncertainties remain where they should. The exact three-dimensional shape is inferred from two-dimensional projections. A prolet halo seen end-on can mimic a more concentrated spherical one, and the reverse can also be true. Modest bulk motions in the gas which add pressure support not captured by temperature alone can bias hydrostatic mass a little low unless accounted for. The dynamical measure, which depends on how galaxy orbits are distributed between radial and tangential families, carries a corresponding model dependence. Even with these caveats, the overlap among methods stays within a comfortable range and the combined picture remains steady. The halo also imprints a subtle effect on the background radiation that fills space. Hot electrons in the intracluster gas scatter background photons, shifting a tiny fraction of them to higher energy. This produces a small change in the brightness of the cosmic microwave background toward the cluster, a shift called the Sunyaev-Zeldovich effect, which depends on the integrated pressure of the gas along the line of sight and thus on how the gas is arranged within the well. Observations of this effect across the cluster provide yet another check on the pressure profile, and by extension on the depth of the dark matter potential that holds the gas. The combined use of lensing galaxy, motions, X-ray pressure, and microwave background scattering ties the structure of the halo to directly observed quantities with few assumptions in common, giving the result a quiet authority. The outer region of the halo is the place where matter in the web first comes under its long influence, and the inner region is the part where the well is deepest and the gas most compressed. Remaining strictly at the cluster scale, the concern here is only with the overall mass and shape, not with the small features that live inside. On this scale, the halo's role is to create a basin that sets orbital times pressure levels and the time it would take gas to radiate away its heat. These times and levels vary with radius in a regular way. They are the background conditions against which later smaller processes act. The dark matter halo is therefore both container and governor. It defines the boundary within which galaxies gather, it sets the field that holds hot gas in place, and it controls the speed at which material can drift inward by setting the gradient of the potential. It changes only slowly with time because most of its mass is collisionless, and because additions at the boundary are gentle on human timescales. The science that underlies this picture aligns with the broader consensus from many clusters studied over decades. Halos follow a family of density curves that change slope from shallow in the centre to steep in the outskirts. Their shapes are often mildly elongated. Their total masses measured by different methods agree when biases are allowed for, and their presence is the primary reason clusters are bound systems rather than short-lived gatherings. The Phoenix cluster fits this frame and gives it a concrete form at its distance and mass. Holding to this radius, the view rests with the sense of a deep, quiet well that dictates structure without noise. The web supplies the contents, the halo holds them. Everything that happens later in smaller regions takes place within this steady field, whose size, mass, and slow evolution give the cluster its long memory and its broad stability. At large radius, the gentle drift along filaments changes character. Infalling gas approaches the cluster's boundary, with speed set by the deepening potential of the dark matter halo. Where that flow meets the already held atmosphere, motion becomes heat. The accepted picture at this scale is simple, and sufficient broad shocks stand in the outskirts and convert a portion of the kinetic energy of the inflowing medium into thermal energy, raising the gas to the high temperatures that fill the cluster interior. A shock is a narrow transition where pressure, density, and temperature jump together. Upstream the gas is cooler and moving inward. Downstream it is hotter and slower, held more nearly in balance by the cluster's gravity. The radius of this transition is not a hard shell. It occupies a broad zone whose exact location depends on the local geometry of infall and on the history of recent minor encounters. Even so, the physical change across it is sharp compared to the slow gradients elsewhere, and it marks the place where external flows become part of the intracluster medium. The inflowing gas is not uniform. Filaments carry material along preferred directions, so the shock is not a perfect sphere. Where a filament strikes the atmosphere, the shock stands closer in and grows stronger along that lane. Between filaments where infall is more diffuse, the shock sits farther out. The strength of a shock is measured by the ratio of upstream speed to the local sound speed. In the true outermost accretion zone, this ratio can be large because upstream gas is still relatively cool and fast. Closer in, where the outer atmosphere is already hot, the shock is weaker. The Phoenix cluster's position within a busy node suggests more than one such transition at different angles, with shapes that reflect the specific pattern of supply. The transformation itself is set by conservation laws. Across the shock mass fluxes, continuous momentum rises, because pressure rises and energy is rebalanced, so that kinetic energy lost from bulk motion appears as heat, with a smaller share deposited into non-thermal components, such as turbulence, and a minority share possibly into relativistic particles. The immediate result is an increase in temperature and entropy. Entropy is a measure of how spread out the heat is for a given density, and it jumps because a shock adds heat in a way that cannot be reversed by simple compression or expansion. This jump is the signature that distinguishes the shocked medium from the still falling gas, and it is the step that prepares the outer atmosphere to settle into the pressure profile described at larger scales. Evidence for these transitions is gathered carefully because the outskirts are faint. X-ray brightness falls with the square of the density, so the view is dim where the gas is thin. Even so, gradual stacks of long exposures reveal edges where temperature rises and density steps down across arc-shaped boundaries in projection. The same regions sometimes show a small change in the spectrum of the scattered background radiation, a subtle imprint of pressure that strengthens just inside the edge. At radio wavelengths, long arcs called relics appear in some clusters near these outer zones. They are believed to trace electrons energized at shocks, and then spiraling in magnetic fields emitting synchrotron radiation. Not every shock displays such arcs, and not every arc sits at the exact edge of the hot atmosphere, but taken together. These signs indicate that broad conversion from motion to heat occurs at the boundary and along in falling lanes. Uncertainties remain in the details as they should. The exact strength of outskirts shocks is hard to fix because projection mixes upstream and downstream emission along the line of sight. If a filament crosses the view, cooler upstream gas can soften a measured temperature jump. If a substructure lies just inside its denser gas, can steepen a surface brightness edge unrelated to a shock. Accounting for these blends requires maps that combine temperature density and pressure with care, and the results carry ranges rather than single exact numbers. Even with these cautions, the presence of transitions remains robust. Density steps, temperature rises, and entropy jumps line up consistently where infall meets the held atmosphere. The outskirts are also where the first signs of interaction between the cluster medium and infalling galaxies appear. As galaxies cross the boundary, the pressure of the hot gas pushes against their own gas. This ram pressure can begin to strip outer reservoirs, laying down faint trails that point away from the direction of motion. The action is mild at this radius and grows stronger inward. At the boundary, it registers as the opening note of processes that later shape the gas content of cluster members. The primary focus here remains on the medium itself, which by passing through shocks takes on the temperature and pressure that define the cluster interior. The geometry of the shock zone carries information about the way the cluster grows. Where filaments supply gas persistently, a quasi-stationary surface stands and is renewed by inflow. Where the boundary has recently been disturbed by a minor subcluster, the surface can ripple with local bulges where material has yet to settle. The timescale for such ripples to damp is long compared with human observation, but short compared with the age of the cluster, so the zone's broad shape tends toward a steady average, even while small features drift and fade. Turbulence arises behind the shock as shear layers and eddies form in the warmer, denser gas. This turbulence adds a small non-thermal pressure that supports the medium slightly beyond what temperature alone would suggest. In the outskirts, this contribution is often a significant minority of the total support, gradually declining toward the centre, where turbulence decays and the gas becomes more stratified. Measuring this support directly is difficult, but comparisons between lensing masses and X-ray masses give indirect limits that are consistent with a modest contribution. The shock also can be a site of mild particle acceleration. Diffusive processes at the transition can push a small fraction of electrons into higher energies. If a magnetic field is present, those electrons radiate and produce the radio arcs already mentioned. The fraction of energy that enters this channel is small compared to the thermal share. The dominance of the thermal path is why the intracluster medium is X-ray bright, and why its temperature follows gravitational depth rather than the varying presence of radio arcs. From a thermodynamic point of view, the outskirts shock sets the initial conditions for everything that follows deeper in. Downstream of the transition, the gas joins the cluster atmosphere, with an entropy set by the strength of the shock and by the temperature of the upstream flow. Over time, repeated passages of gas from different angles fill the outer layers with material that shares a similar entropy flaw, and this flaw sets how far inward any parcel can sink without further heat loss. In this way, the boundary exerts control over the slow settling of the interior without needing to appear as a sharp structure in every observation. The transition is not the only edge-like feature in the outskirts. Contact discontinuities called cold fronts also exist where gas at different temperatures slides past with little mixing. These are not shocks. Pressure stays continuous and only density and temperature change. They mark past motions of cooler clumps within the hot medium. Maintaining the focus on the place where inflow becomes heat, it is enough to note that both types of features can appear in nearby arcs, and that distinguishing a shock from a cold front requires temperature and density on both sides, not brightness alone. Doing so correctly ensures that the role of shocks in heating the outer atmosphere is neither overstated nor missed. The region remains quiet in the sense that strong violent events are rare at this radius. The transformation is powerful but steady, carried by broad inflow and governed by gravity rather than by sudden explosions. The energy budget is large, yet the rate of conversion per unit volume is low because the gas is thin. This is why the outskirts are faint in X-rays, and why long integrations are needed to trace the gradients. The same thinness makes the region especially useful for measuring pressure through the scattered background radiation, because contamination from bright central structures is lower. Holding to this radius, the sense of structure changes from the alignment of distant filaments to the presence of a bound atmosphere with a moving edge. Outside matter follows the web's long, slow paths. Inside, gas begins to share a common pressure field and to settle into a profile set by gravity and by its own heat content. The shock mediates the passage between these two regimes, adding heat at just the rate needed to keep the outer atmosphere in the temperature range seen in clusters. Where the shock is stronger, the downstream temperature is higher. Where it is weaker, the outer layers are slightly cooler and will require gradual compression and gentle mixing to reach the interior average. The Phoenix cluster's boundary, viewed through this lens, is not a single ring, but a zone of conversion whose location and strength vary with angle and with time. The overall effect is steady and fell slows temperatures rise, entropy increases and the gas becomes part of the cluster. Remaining strictly at this region, the description pauses with the picture of a broad, faint edge that turns motion into heat across many directions at once, setting the first thermodynamic step for the atmosphere within. Inside the boundary, the atmosphere becomes continuous, a thin sea of hot plasma that fills the volume between galaxies. This medium is made of electrons and ions moving fast enough that atoms cannot remain bound. Temperatures lie in the range of many tens of millions of degrees Celsius. At such heat, the gas shines in X-rays, not by lines alone, but by a smooth glow produced when electrons are deflected by ions and radiate a little energy each time. This process builds a broad spectrum that strengthens where density is higher and where the path through the gas is longer. Against that smooth light, fainter features from heavy elements appear as lines. Iron, silicon, sulfur, and other products of many generations of stars add small peaks to the spectrum. The presence of these elements shows that the intracluster medium is not pristine. Over long times, winds from galaxies and the deaths of stars have mixed their material into the cluster's atmosphere and carried it far from where it was made. The plasma is nearly weightless to the eye, yet it is the largest single baryonic component by mass in the cluster. Its pressure supports it against the gravity of the dark matter halo. On large scales, the gas rests close to hydrostatic balance, inward pull balanced by outward pressure gradient. Where pressure falls with radius, the atmosphere remains held. Where density declines, X-ray brightness softens. Temperature does not need to be the same everywhere. It often declines gently from a broad peak outside the very centre toward the outskirts, reflecting the way shocks and compression have heated the gas, and the way it slowly cools as it expands into shallower regions. At these radii, cooling by radiation is slow compared with the age of the system, so most parcels keep their heat and drift only gradually along the background gradient set by the halo. The plasma is not a perfect fluid. Particles travel long distances between direct collisions compared with the smallest scales one might imagine, yet magnetic fields thread the gas and tie-charged motion to field lines. This makes transport of heat and momentum anisotropic easier along the local field than across it. The effective viscosity and thermal conduction depend on the tangled geometry of those fields, and on small instabilities that arise when temperature or pressure vary along them. The result is a medium that can carry sound waves and weak compressions across large distances, can damp turbulence over time, and can keep sharp boundaries such as cold fronts intact longer than a fully collisional gas would allow. The fields are weak in absolute strength, but strong enough in this thin environment to matter for how the gas behaves. They also polarize radio emission from embedded sources, allowing the rotation of polarization to act as a probe of field strength and distribution through depth. The X-ray glow does more than reveal presence, it measures state. The brightness gives density, the spectrum gives temperature. Together they give pressure and entropy. Entropy rises outward, not because heat is added there now, but because the outer layers were shocked earlier and have not cooled since. This outward rise is a stable configuration. It resists large-scale convection and helps keep the atmosphere stratified. Small motions remain. Gentle sloshing stirred by old encounters can shift isotherms and create contact edges where density and temperature change but pressure does not. Modest turbulence can add a non-thermal share to the support, but in many well-settled clusters this share is a minority compared with thermal pressure. Indirect measures that compare the total mass from lensing with the mass inferred from pressure suggest that turbulence and bulk flows together, add only a small fraction of the needed support in much of the volume outside obvious disturbances. The intra-cluster medium also imprints itself on the background radiation that bathes the universe. Hot electrons scatter a small portion of background photons to higher energies, producing a decrement at some wavelengths and an increment at shorter wavelengths. Maps of this effect show pressure directly rather than density squared, so they complement X-rays by highlighting regions where pressure is high, even if density is not. Combined maps from both methods trace the three-dimensional structure and projection more completely than either can alone. A lesser-known detail is the presence of a faint population of warm gas that coexists with the hot phase. It appears as weak extended emission at optical and ultraviolet lines over tens of thousands of light-years in some clusters, and as faint absorption systems in rare, fortunate sightlines. This component is too cool to shine strongly in X-rays, and too warm to be part of the cold clouds nearer the centre. It likely arises where turbulent mixing and conduction blur the boundary between hot atmosphere and denser structures, creating layers at intermediate temperatures. It carries little mass compared with the hot phase, but plays a role in how energy and material pass between phases. Uncertainties sit where they should. The exact level of thermal conduction across tangled fields is not fully known, and may vary from place to place. Micro instabilities in the plasma can suppress or enhance transport in ways that global models must approximate. The amount and spectrum of turbulence differ among clusters, and within a given cluster over time, leaving ranges rather than a single number for non-thermal support. Even with these uncertainties, the broad picture holds the gas is hot-thin, stratified by entropy, and close to hydrostatic balance within the halo. Ironies remain soft and practical. Only took the thinnest medium in a galaxy system to carry most of its ordinary mass. Only took light that we cannot see with human eyes to show the clearest image of the atmosphere that binds the cluster. Only took weak magnetic fields to guide the behaviour of a sea so hot that atoms cannot exist. The chemical content of the plasma is a quiet ledger of past activity in the cluster population. Iron-rich cores and gentle radial gradients in element ratios tell of contributions from both short-lived massive stars and longer-lived systems. The wide spread of metals across hundreds of thousands of light-years shows that stirring and outflows have acted for a long time to carry products of stars into the intracluster medium. The distribution is not uniform, but smooth enough that the broad abundance pattern can be read in X-ray spectra with patience and long exposure. The medium supports waves that cross the volume without large dissipation when wavelengths are long. These waves carry energy and information, and can slowly spread disturbances across the atmosphere. Weak, wide ripples in X-ray brightness at large radius are one sign of such motions. Their presence does not require strong drivers now. The atmosphere itself, once set in motion by earlier events, can take many tens of millions of years to relax fully. Remaining at this scale and not advancing inward, the description holds on the way the hot sea shapes, and is shaped by the cluster's gravity. Pressure gradients carry the memory of shocks at the boundary, and of the slow compression that deep wells impose. Entropy stratification keeps the medium layered and stable against overturning. Magnetic fields permit sharp interfaces and limit mixing while still allowing long-range communication along field lines. Heavy elements record enrichment by generations of stars and the quiet circulation that spread them. X-rays and scattered background light act as two complementary windows, one sensitive to density, one to pressure, that together lay out the structure without the need to assume a single state everywhere. The galaxies drift within this sea, their motion slowed a little by the drag of the medium, their own gas shaped by the pressure they encounter, but those interactions belong to nearer regions and different scales. Here the focus remains on the continuous atmosphere itself, which fills most of the cluster's volume and sets the conditions for any process that takes place inside. The hot plasma is the context. It holds its place with slow change, bright enough to chart, thin enough to flow, and ordered enough to keep its broad gradients for a long time. Pressure does not fall at random with radius. It follows a smooth path that reflects the weight of gas above each layer, and the depth of the dark matter well below it. Entropy does not rise by chance either. It increases outward because gas that entered earlier and was heated at the boundary now sits at larger radii with more heat per particle for its density than gas deeper in. These two profiles, pressure decreasing and entropy increasing, set the character of the intracluster medium at every distance from the centre. They also set a clock. The clock is the cooling time the span a parcel of gas would need to radiate away its heat at its present density and temperature, if nothing reheated it. Where density is low and temperature high, radiation is slow and the clock runs long. Where density rises and temperature eases, the clock shortens. This time is read from the same X-ray spectrum that gives temperature and density, because the power radiated per volume depends on both, and on the mix of elements. At the temperatures that dominate most radii, the glow is mainly from electrons slowing in the fields of ions, a process that changes slowly with temperature but quickly with density, while closer in lines from heavy elements begin to add more power. The combination makes the cooling time fall sharply toward the centre in many clusters. The Phoenix cluster follows this general pattern with strong contrast between outer and inner radii. Pressure at large distance supports the gas gently against gravity and entropy. There is high enough that parcels cannot sink without giving up heat. Moving inward by tens to hundreds of thousands of light years, pressure grows, density rises, and entropy drops in a curve that can be described with a simple function. The details of the function matter less than the trend. Smaller entropy means gas can in principle drift inward if it can lose heat. Higher density means it can lose that heat more quickly. The cooling time therefore tracks the entropy profile closely, taking large values outside and falling steadily inward toward values that are shorter than a cosmic age in the central region. The intracluster medium is stratified by these clocks. In outer layers, the time to radiate is longer than any other relevant timescale. There the gas keeps its heat and behaviour is set by gravity and pressure gradients. Closer in, the cooling time becomes comparable to a few billion years, then to a few 100 million years, and finally to even shorter spans near the core. The Phoenix cluster is notable among massive systems for reaching very short cooling times in its central tens of thousands of light years, but remaining at this region the point is general. A falling clock makes inward drift and condensation possible. A lesser-known detail sits in the way observers combine cooling time with another local measure to gauge where the condensation begins. The other measure is the freefall time, the time a small blob would take to drop a short distance if pressure could not support it. The ratio of cooling to freefall sets a simple test when cooling is much slower than falling disturbances are smoothed. When cooling is only several times longer than falling small, overdensities can shed heat, grow denser and decouple from the hot phase. Maps that compare these times in relaxed clusters show broad rings where the ratio falls to values of about 10 or lower, and those rings often coincide with places where warm and cold gas later appears. The Phoenix cluster's inner profile passes through such ratios, indicating that the thermodynamic conditions for multi-phase structure exist. The profile picture is not perfect in detail, because transport along tangled magnetic fields complicates the path to condensation. Thermal conduction can carry heat inward along field lines and slow the fall of the cooling time. Turbulence can mix layers and spread heat as well. Both effects can lengthen the clock locally without erasing the overall trend. Measurements that compare the pressure implied by X-rays with the total mass from lensing suggest that turbulent pressure support is not dominant in much of the volume, but even a modest share can change local stability. Uncertainties remain in the exact size of conduction across field tangles and in how micro-instabilities in a weakly collisional plasma shape it. These are active topics, and global models include them with ranges rather than with a single fixed value. The entropy profile contains a quiet record of the past. If gravity alone had heated the gas during assembly, the curve would be smooth all the way to the centre. In many massive clusters, the inner entropy flattens instead, as if some process has limited how low it can fall. That process can be gentle stirring and weak shocks from a central engine that reheat gas just enough to hold it off the very bottom of the well. The Phoenix cluster shows a deep central decline despite signs of reheating at small radii, a combination that emphasises how strong the inward cooling drive can be when densities are high. Remaining at the scale of radial profiles rather than specific features, the important point is that the inner entropy minimum and the short cooling times together define an environment where gas is ready to change state if heating does not match losses. Pressure also carries information about subtle motions, where small ripples or weak concentric edges appear in maps of surface brightness. Corresponding small variations in pressure can be derived. These features travel outwards slowly as sound waves or weak shocks, and can distribute energy over wide angles. Their presence implies that the atmosphere communicates disturbances from the centre to larger radii, and that part of the radial pressure gradient is maintained not only by static balance, but also by the slow passage of waves that damp over long distances. The cooling clock responds to such energy transport by stretching slightly where a wave has recently passed, and by contracting slightly in the zones between ripples. The broad gradient remains. Ironies stay soft and practical. Only took a thin atmosphere to keep the clearest time in a giant system where density rises, the clock runs faster. Only took a rising entropy outward to prevent large-scale overturning in a sea that otherwise would be free to mix. Only took a comparison of two simple times, cooling and falling, to outline where complex multi-phase structure prefers to grow. The measurement of cooling time depends on composition, because heavy elements add line emission at central temperatures, and the Phoenix cluster's inner atmosphere is enriched by material from many stars over long periods. Abundance gradients therefore matter in the final numbers. Observers account for this by fitting spectra that include lines from iron and other elements summing their contribution with the smooth continuum. The result is that the inner cooling clock is even shorter than a pure continuum would predict, a fact that quietly links the history of star formation and supernovae in the cluster population to the present state of the gas. The profiles also offer a way to estimate how much mass would cool if nothing heated the gas. Integrating the radiative power over shells and converting that power into a mass loss rate gives a notional flow inward, often called a cooling flow. In practice, the amount of cold gas and the rate of new stars do not match the full notional rate, which implies a source of energy that offsets most of the losses. Even so, the notional flow remains a useful upper bound and a reminder that the profiles alone predict substantial condensation where clocks are short. The Phoenix cluster's inner profiles set one of the largest such bounds among nearby massive clusters, a point that will matter at smaller radii. Remaining here, the view ends with the profiles themselves, pressure that falls gently outward, entropy that rises, and cooling time that drops toward the centre until it reaches values short enough to invite change. These functions are not decorative. They are the slow instructions that the atmosphere follows. They fix how far a parcel can sink, how quickly it would lose heat, and whether small disturbances can grow. They explain why the outer gas is quiet and held, and why the inner gas is ready to transition to new phases if not reheated. The cluster keeps these gradients for long periods, because the well that sets them evolves only slowly. Within that stability, the clocks continue to turn, and the atmosphere moves inward a little at a time wherever the time to cool allows it. Within the broad atmosphere, edges appear that are not shocks. They are smooth boundaries where denser cooler gas lies beside thinner hotter gas, while pressure remains nearly the same on both sides. These are cold fronts. Each front is a contact surface that marks motion of gas within the cluster, rather than new heat being made. In X-ray images, they show as arcs where brightness rises suddenly, because density jumps and spectra across the same arcs show that temperature falls just as the brightness increases. Pressure found by combining density and temperature changes little across the boundary. The pattern means that a block of cooler gas slides through its surroundings, with minimal mixing protected by its own pressure balance. Many clusters show such fronts, and the Phoenix cluster carries them as curved lines that repeat at different radii. The origin is gentle, a minor gravitational nudge often from a small subcluster that passed nearby in the past, displaces the central gas from the bottom of the potential well. The gas then begins to oscillate around the minimum. This motion, called sloshing, winds the displaced layers into spiral-like flows that wrap around the centre. As they turn, interfaces between layers of different temperature sharpen into fronts. The pattern spreads outward over time as each swing of the gas launches a new arc at a larger radius. The field that holds the cluster sets the pace. The atmosphere responds as one large stratified fluid. The sloshing does not tear the cluster apart. It repositions gas and moves heat sideways without strong shocks. In projection, the fronts often draw partial circles that can be traced over tens of thousands of light years. Some clusters show a faint spiral of increasing radius, in which each arc matches the next in curvature and spacing. The Phoenix cluster follows this family of shapes with edges that are brightest on one side of the core, and that line up into a slow sweep when map contours are viewed together. The fronts are thin compared with their radius, which implies that mixing and diffusion across them are modest. Magnetic fields help. As a cool block moves through hotter surroundings, field lines can wrap around its leading face, a configuration that stabilizes the interface and suppresses small instabilities that would otherwise wrinkle and mix the boundary. This magnetic draping is weak in absolute strength, yet effective in a plasma where particle paths are long, and where motion along field lines is easier than across them. The result is an edge that holds its sharpness over large angles. Thermal conduction is likewise limited across the front, or else the temperature step would smooth out quickly. Observations that compare the width of fronts to the distance heat could have spread in the time, since the displacement suggests that conduction across tangled fields is strongly reduced from the simplest expectations. The fronts therefore act as sliding lids that separate layers for long intervals. Sloshing moves more than heat. It also transports the chemical traces that heavy elements leave in the gas. Enriched material that once sat near the centre can be carried outward along the spiral path, and less enriched material can be drawn inward on the return flow. Maps of element abundance in some clusters show arcs that track the fronts, with higher values along the inside of a curve and slightly lower values just beyond it. The pattern is subtle, and requires long exposures to see, yet it shows that sloshing quietly redistributes metals without fully mixing them. This same drift spreads entropy, laterally slightly lower entropy gas rides outward along the spiral, while slightly higher entropy gas is carried inward alongside it all at nearly constant pressure. The overall radial profiles remain intact. only small ripples are added around them. The motion carries a measured pace. Fronts propagate outward at speeds well below the local sound speed, so pressure waves from the displacement can move ahead and smooth conditions farther out even while the contact boundary takes longer to arrive. In some systems, week-wide ripples in surface brightness accompany fronts and record this communication. These waves carry little dissipation and spread energy over broad areas without strong heating. The Phoenix cluster's edges fit this quiet picture: crisp arcs, modest pressure change, and surrounding zones that remain ordered. Uncertainties remain in the exact three-dimensional shapes. Projection can lay two edges along the same line of sight and make a single arc look stronger, or hide part of a spiral if it lies behind brighter gas. Determining whether a given boundary is entirely a cold front or has a weak shock nested nearby requires both temperature and density on both sides measured with care. Allowing for these limits, the classification in well-observed regions remains secure. Pressure-continuous fronts dominate and outline sloshing paths. A lesser-known detail is the small shear layers that can form just outside the leading face of a front. Where velocity differences are strongest instabilities, like the Kelvin-Helmholtz mode, would normally roll the edge into waves and mix the gases. The relative smoothness seen in many fronts implies that either viscosity or magnetic tension suppresses these rolls. Measuring the degree of suppression offers an indirect window on the plasma's effective viscosity, and on the field geometry. In places where small billows do appear, their size can set limits on how much stabilizing influence is present. In the Phoenix cluster, the general smoothness of the edges suggests that suppression is common, with only small patches showing signs of partial roll-up. The effect of sloshing on the cluster's thermodynamics is cumulative rather than dramatic. By moving cooler gas sideways and outward, it delays direct sinking of that gas towards smaller radii. By bringing slightly warmer gas inward along neighbouring paths, it spreads heat without destroying stratification. In this way, the process exchanges energy between nearby radii without erasing the larger gradient. The net result is that cooling times at a given radius can lengthen slightly, where low entropy gas has been shifted away, and shorten slightly where it has been brought in. These changes are small compared with the overall trend, but are real and measurable. They testify to the role of gentle dynamics in shaping conditions over tens of thousands of light years. The fronts also interact with the galaxies that move through them. A galaxy that passes across a front encounters a sudden change in external pressure and temperature. Its own gas responds, perhaps tightening a stripped tail or altering the rate at which its outer layers are removed. The dominant story at this radius remains the atmosphere itself, but the presence of edges adds structure to the medium that member galaxies feel. Even so, the bulk motion is small compared with orbital speeds, and the primary forces on galaxies come from the overall pressure and from gravity. Sloshing has a long memory and a slow fade. A single encounter can set the central gas oscillating for hundreds of millions of years. Each swing weakens as viscosity and weak turbulence remove kinetic energy. The spiral pattern broadens and its contrast falls, yet traces remain for long times, especially where magnetic draping kept edges thin. Later, minor encounters can renew the motion and lay fresh arcs over older ones. The patchwork of fronts at different radii is therefore a record of several small events rather than a single episode. Reading that record requires matching curvature, brightness, and temperature steps into a plausible sequence of displacements and returns. The Phoenix cluster shows the marks of such a sequence in a way consistent with a calm, long history, punctuated by modest nudges rather than recent disruptive mergers. Remaining strictly at this region, the view holds to the moving boundaries themselves. They are signs of ordered motion in a stratified atmosphere. They shift heat and composition laterally while preserving pressure balance. They reveal the role of magnetic fields and limited transport in maintaining sharp interfaces. They hint at the past by the way their arcs nest and by the directions they point. They do not overturn the cluster or erase its profiles. They add detail to a stable structure and keep that detail for long enough that the edges can be mapped and followed. The atmosphere seen this way is not still water. It is a slowly turning basin in which layers glide past one another, along curved paths separated by clean contact surfaces that hold shape as they move. The description pauses with those arcs in place, their temperatures stepped, their densities balanced, and their paths traced across the inner atmosphere like quiet currents that leave the larger sea unchanged. Across the hot atmosphere, the faint lines of heavy elements write a quiet history of how matter moves and where it came from. These elements iron, silicon, sulfur, oxygen, and others are forged inside stars and released by supernovae and gentle galactic winds. They do not originate in the intracluster medium. They arrive there mixed and carried outward from galaxies over long spans of time. The Phoenix cluster's X-ray spectrum carries these fingerprints as small peaks laid on the smooth glow of hot electrons. By measuring the strength of those peaks against the continuum, maps of abundance appear. They are not uniform. Broad gradients emerge with higher values toward the centre and lower values farther out, and with subtle arcs and patches that follow the gentle motions already described. Each pattern is a marker of transport. The sources are several and steady. Short-lived massive stars explode as core collapse supernovae and release oxygen, neon, magnesium and silicon. Older, longer-lived systems yield Type Ia supernovae that add iron and nickel at a measured pace. Both families act within galaxies that live in the cluster. Over time, stellar winds and supernova-driven outflows push part of this enriched gas beyond galactic halos and into the intracluster medium. Ram pressure felt by galaxies moving through the hot atmosphere strips part of their gas and releases it as trails that later mix away. Outflows from a central active nucleus, when present, stir and lift enriched material from the brightest cluster galaxy and spread it along radio-inflated channels. None of these processes acts like a strong explosion at the cluster scale. They are slow, repeated and cumulative. The result is a sea whose chemical content quietly records many small contributions. The abundance pattern is read in ratios as well as in totals. Where the balance of oxygen to iron is high, core collapse supernovae have contributed strongly. Where iron rises relative to alpha elements, the imprint of Type Ia explosions grows. In many massive clusters, the inner tens of thousands of light years show an iron peak that sits on a broader plateau of alpha elements. This is the signature of long enrichment by older systems near the centre, layered on top of wider earlier contributions from short-lived stars across the cluster. The Phoenix cluster follows this family of patterns with enriched gas drawn into arcs and lanes by sloshing and by the wide circulation within the hot atmosphere. The subtlety of these maps requires patience. X-ray photons from lines are far fewer than those from the continuum, and their strength depends on temperature as well as on composition. Spectral fits therefore allow temperature and abundance to vary together across many regions and return values that come with honest ranges. Even within those ranges, consistent features emerge. A gentle decline of abundance with radius shows that mixing has carried metals far from galaxies, but not so completely as to erase the central enhancement. Fainter ridges of higher metallicity align with contact edges and with channels lifted by radio cavities, indicating that motions within the atmosphere redistribute heavy elements along preferred paths. The physics of that redistribution is quiet. Turbulent diffusion acts over long times to broaden gradients. Sloshing carries low entropy enriched gas outward as narrow streams while drawing less enriched gas inward alongside. Magnetic fields limit mixing across sharp interfaces, allowing abundant steps to persist where cold fronts hold. Weak sound waves carry little mass but help stir gas between fronts. Conduction moves heat more easily than it moves matter, so composition changes are slower than temperature changes. Over hundreds of millions of years, the combined effect of these processes distributes metals across scales of hundreds of thousands of light years without flattening the profile entirely. A lesser-known detail sits in the outer atmosphere where the metal content remains measurable even at large radii. This level speaks to early enrichment, likely when galaxies and groups were smaller and winds more effective at moving material into the shared medium. The presence of a flaw far from the centre tells that the cluster's gas has been processed by stars through most of cosmic time, and that today's transport only refines a distribution laid down long ago. In the Phoenix cluster, the outer metal content stays above zero by a comfortable margin consistent with a long record of gentle circulation. The transport also moves dust in small amounts. At high temperature, dust grains do not last. They sputter and return their elements to the gas. Near cooler structures, dust can survive longer. Optical images of some clusters show faint dusty filaments in the central regions, and traces of that dust can align with lanes of higher metallicity in the surrounding hot medium, as if the same flow that draws clouds inward also marks the atmosphere with the chemistry they carry. Where those lanes rise along the paths of buoyant radio bubbles, the alignment indicates that feedback from the central engine does more than heat. It lifts enriched gas and spreads it through the core. The Phoenix cluster's chemical map shows this kind of quiet uplift and drift, not as a single plume, but as several channels braided through the inner atmosphere. Uncertainties are clear and remain in place. The exact conversion from line strength to abundance depends on atomic data and on the temperature structure within each region. Multi-temperature gas can bias a single temperature fit, especially where cooler components add line power. Careful analyses mitigate this by allowing a small range of temperatures in each spectral extraction, and by comparing results across instruments with different responses. Even with these cautions, the large-scale picture holds. Enrichment rises toward the centre, remains measurable far out, and follows arcs that mirror known motions in the hot atmosphere. The iron peak near the core aligns with decades of star formation in the brightest cluster galaxy, and with slow input from type supernovae in its old stars. Alpha elements spread more broadly, consistent with early cluster-wide contributions. The chemical gradients carry thermodynamic meaning. Heavy elements increase the efficiency with which gas radiates at central temperatures, because line emission adds to the smooth glow. Where abundance is higher, cooling times shorten further, all else being equal. This effect is modest in the outer atmosphere and grows toward the centre, where densities and metallicities are both higher. Thus, composition and cooling reinforce each other in the inner regions. Remaining at the current scale, the point is simply that the chemical map and the cooling time map resemble one another more than chance would allow, because both trace the long action of galaxies on the gas. Ironies stay quiet. Only took the faintest lines in an X-ray spectrum to reveal the movement of matter across distances that no star's light can cross. Only took slow processes, winds stripping up lift to write a global chemical pattern that outlives the galaxies that launched it. Only took weak magnetic fields and limited mixing to preserve signatures strong enough to be drawn as contours across a sea so thin that a breath of room air contains more particles. The circulation that sets these patterns also sets a limit on how sharply abundance can peak. Where motions are gentle, a central maximum survives. Where they are strong, it broadens. The Phoenix cluster, with ordered sloshing and buoyant channels rather than violent mergers, keeps a prominent but not singular peak with ridges that trace the paths of moved gas. The outer plateau set early remains. Between them, a smooth decline carries the memory of diffusion and drift. The view holds here, following chemical clues toward the core without yet entering it. Abundance rises, arcs align with edges and ridges mark lifted lanes. The history written by stars in many galaxies now resides in a single atmosphere. Over long times, each small contribution has been carried mixed and arranged into gradients that guide where cooling can quicken and where gas will hold its heat. The cluster keeps this chemical order with slow change, and the map of heavy elements remains a quiet record of how the hot sea has moved and how galaxies have fed it. Toward the centre, the atmosphere changes character. Pressure rises, density climbs, and the time for gas to lose its heat by radiation falls from spans longer than the age of clusters to spans shorter than a human lifetime in astronomical terms. The inner region measures only a few tens of thousands of light-years across. Here, the intra-cluster medium no longer behaves as a single hot phase that simply holds its place. its thermodynamic clock runs quickly enough that parcels can shed energy slip to lower entropy and begin to separate from the surrounding sea. The change is read from the same X-ray spectrum that outlined the outer layers. At these radii, line emission from heavy elements strengthens, adding to the smooth continuum and making total cooling more efficient. Temperature profiles bend downward, not into coldness, but into values lower than the broad peak found farther out. Density rises steeply. Combined, these trends drive the cooling time down by orders of magnitude from its outer value. The result is a core in which gas can condense. Cooling does not proceed as a single stream from hot to cold. It steps through intermediate states, where a parcel loses enough heat that its pressure would otherwise drop it, compresses under the weight of overlying layers, making cooling faster still. If local conditions permit, small overdensities grow and detach gently from the background. In a stratified magnetized plasma, this detachment is guided by field lines that limit motion across them, and by the balance between radiative losses and heat supplied by conduction and weak stirring. The wake of this process is a mixture hot background dotted with warmer clumps shading into clouds cooler still. The Phoenix cluster's centre sits firmly in this regime, with metrics that pass commonly used thresholds for instability over extended volumes. The onset of condensation is most clearly mapped by comparing two times. One is the cooling time already described, the other is the freefall time, the period a small perturbation would take to drop a short distance in the cluster's gravity if it were not held by pressure. Where cooling time remains much longer than freefall, small disturbances are erased before they can lose enough heat to break away. Where cooling time falls to only several times, the freefall time density fluctuations have time to radiate compact and persist. In the Phoenix cluster, the ratio of these times falls to values near and below the commonly cited threshold over large parts of the inner tens of thousands of light years. This tells that the conditions for a multiphase core are present across significant angles, not only along special paths. The structure that emerges is supported as much by pressure as by gravity. Even while cooling, each parcel remains close to local balance. Pressure does not collapse at once. Rather, temperature and density trade as heat escapes, and the parcel maintains approximate pressure equality with its surroundings until it becomes sufficiently cool and dense to behave like a distinct cloud. Conduction along magnetic field lines can slow or even halt this path by importing heat from nearby hot gas, and turbulence can blend layers before contrasts build. In practice, both effects operate but do not erase the gradient where cooling is rapid, and where field geometry limits cross-field transport. This balance between losses and small sources of heat explains why condensation is patchy and filamentary, rather than uniform. A lesser-known detail sits in the way the shortest cooling times cluster at the bottoms of gentle potential valleys within the core. The dark matter halo is not perfectly spherical, and the distribution of old stars in the central galaxy adds a small centrally concentrated contribution to gravity. The combined field defines a network of shallow basins where gas can settle while it cools. X-ray maps that convert brightness and temperature to pressure and entropy show troughs that line up with the places where warm and cold phases later gather. The alignment suggests that geometry as much as microphysics guides where condensation proceeds most readily. The core also supports slow waves and weak shocks that move outward from the very centre. These disturbances, seen as faint ripples in surface brightness, carry energy across the inner atmosphere and can gently thicken the core's entropy floor. Their passage modifies the cooling time field by small amounts, lengthening the clock where a crest has added a touch of heat and shortening it between crests. The overall tendency remains downward, but the pattern gains texture. This texture corresponds to the mottled appearance of intermediate temperature traces in deep maps, a sign that the core is not uniform even on scales well below the radius of the cooling region. Uncertainties remain where they should. The exact level of thermal conduction in the core depends on how tangled the magnetic field is, and on micro-instabilities that can suppress heat flow across sharp temperature gradients. Measurements of cold fronts elsewhere in the cluster suggest that cross-field conduction is limited, but the degree of limitation can vary with radius and with time. The strength and spectrum of turbulence which set how quickly structures mix and how momentum is transported are also measured indirectly in carry ranges. Even with these uncertainties, the indicators of short cooling time and low entropy are robust. The centre sits in a state that favours condensation, and observations across several bands confirm that the hot phase coexists with warmer and colder material. The transition through temperatures unfolds in steps that instruments trace in different ways. Ultraviolet lines mark gas at several 100,000 degrees. Optical lines trace material near 10,000 degrees. Millimetre lines from molecules indicate clouds at only tens of degrees above absolute zero. In the core, these signs overlap in projection, and careful subtraction shows that they are not fully coincident. The cooler phases lie along paths where the time ratio is smallest, and where pressure support can carry them without immediate disruption. Each phase carries only a small fraction of the total intracluster mass, yet in this region the amounts become large enough to dominate the local picture. The hot phase communicates with these cooler structures. Conduction along field lines can supply heat to the outer skins of clouds, maintaining thin layers at intermediate temperature. Mixing at their edges creates small parcels that are neither as hot as the background nor as cool as the interiors. These layers radiate efficiently and help the core shed energy without requiring that all gas drop to the coldest state. In this way, a multi-phase medium can cool more effectively than a single phase, but redistributing energy across temperatures rather than removing it only at the bottom. Ion lines strengthen toward the centre and further shorten cooling times. This chemical effect is modest at large radii and strong in the core, where both metallicity and density are high. The result is that places already primed to condense by low entropy, and short times become even more susceptible once composition is accounted for. The pattern in the Phoenix cluster shows concentric regions where the combination of high abundance and high density moves the clock from hundreds of millions of years to far shorter spans. The core in this sense is an engine for phase change driven by its own thermodynamic state. The geometry of the inner potential and the presence of weak motions add order to that change but do not remove its basic cause. Remaining strictly at this scale, the description does not follow the cooler gas beyond its immediate context. It notes only that the core hosts hot, warm and cold phases in close proximity, that the transitions between them are maintained by pressure balance and limited transport, and that their existence is a direct response to short cooling times set by density, temperature and composition. The atmosphere here is not collapsing, it is stratifying. Hot gas still dominates the volume and the pressure support. Cooler structures thread that volume where conditions permit occupying a small fraction of space, but a significant share of attention, because they demonstrate that the core has crossed from a single phase state into a layered one. The picture holds a central region only a few tens of thousands of light years wide, an entropy minimum, a cooling clock that runs quickly, and a quiet separation of gas into several thermal states that remain in pressure balance. The cluster keeps this configuration for long periods compared with human time, yet it is not static. Slow motions, weak waves, and the geometry of the potential continue to rearrange the places where condensation prefers to proceed. The scene ends at this radius, with a core that is fully awake in thermodynamic terms. Cooling as efficient phase separation is present, and the hot atmosphere has begun to share its space with cooler structures that it still supports. Threads appear in the core. They are long, narrow filaments that stretch for many thousands of light years through the hot atmosphere, carrying cooler gas and dust in lanes that curve around the centre. Each filament looks thin against the background, yet each holds multiple temperatures at once. A spine of cold molecular gas only a few tens of degrees above absolute zero. A skin of warm material near 10,000 degrees, and a sheath of intermediate layers that share heat with the hot sea around them. The lines are not straight. They arc and branch, guided by gravity and by magnetic fields that help them keep shape. They do not collapse into stars at once because pressure support and field tension hold them, and because heat from the surrounding medium reaches their surfaces and slows the fall. The presence of dust inside these lanes is clear where they cross starlight and draw faint dark threads against the smoother glow of the central galaxy. Dust survives longer here than in the open hot gas because temperatures inside the filaments are low, and because surrounding layers shield grains from sputtering. The dust mixes with cold molecules and carries heavy elements that formed in earlier generations of stars, a small reminder that this cool phase is made from gas that has lived inside galaxies before. The filaments are not isolated cords. They join in knots where several lanes meet, and they taper into small clouds that drift nearby. In projection, the network outlines gentle spirals and radial fans that begin near the smallest radii and reach outward into the domain where the hot phase still dominates every measure of volume. These shapes echo the slow motions of the core sloshing that bends paths into curves, buoyant channels that lift gas along the sides of cavities and shallow potential valleys that collect condensed material. The lanes drape around these features as cloth would drape over low hills and shallow basins, an image used here only to fix the geometry. The gas inside the filaments moves slowly. Measurements of line widths in the warm and cold phases show speeds well below the sound speed of the hot atmosphere. These speeds vary along a lane, widening near knots and narrowing in the thinner stretches. The pattern suggests ordered motion rather than random agitation. Gravity draws the densest parts downward along the filament axes, while the hot medium pushes back with ram pressure, and magnetic fields resist bending and shear. The result is a near balance that allows long structures to persist without tearing. Where lanes arc around the centre, centrifugal terms add another small support, letting clouds travel on curved paths rather than falling straight in. The surfaces of the filaments are active. Heat flows in along magnetic field lines from the hot atmosphere, and meets gas that can radiate efficiently. Thin layers form where temperatures sit between the core's extremes. In these layers, atoms and molecules are excited and cool by emitting lines at optical and ultraviolet wavelengths. This mixing and conduction operate gently, so the layers remain thin compared with the widths of the filaments, but their total area is large because the network is long. They act as radiators that help the core shed energy without needing every parcel to reach the coldest state. In this way, the presence of filaments changes how cooling proceeds, by providing surfaces on which energy can be lost steadily. A lesser-known detail rests in the magnetic skeleton that holds the lanes narrow. Polarized emission from the warm gas and Faraday rotation of radio waves that pass through the core show fields, aligned along the filaments over large fractions of their length. The field strength is modest in absolute units, but sufficient to provide tension that resists the growth of small instabilities. This alignment also channels heat flow, making conduction anisotropic fast along the lane, slow across it, and thereby protecting cold cores from rapid evaporation. The same fields allow a small share of cosmic ray pressure to gather with the gas. That share is not dominant, yet it can add to support in places where gravity and thermal pressure alone would not hold a long thin structure. The lanes are chemically rich. Molecules such as carbon monoxide mark the coldest parts, while lines from oxygen, nitrogen and sulfur mark the warm skins. Abundance ratios follow those of the intracluster medium and the central galaxy, showing that the material condensed from the same enriched atmosphere rather than arriving as pristine gas. The dust inside carries a similar record and reddens starlight in narrow streaks where the lanes cross the face of the brightest cluster galaxy. These streaks are faint but traceable, and they align with the gas network seen in emission, confirming that the coldest phase sits at the core of each line. Pressures inside the filaments remain close to those of the surrounding hot phase when measured across the cold, warm and intermediate layers. This near equality indicates that the lanes are not overpressured explosions or underpressured voids. They are condensations held in the common field, stitched into the atmosphere rather than detached from it. Where a filament passes near a cavity inflated by radio jets, It often curves along the cavity's rim. This geometry speaks to uplift buoyant bubbles rise through the hot gas and carry cool material with them from small radii to larger ones. The rise is slow enough that the lanes do not break. Instead, they stretch and their surfaces continue to radiate, leaving bright rims of warm gas, where the field and the flow have pressed a narrow band against the hot sea. The Phoenix cluster shows several such alignments with lanes that drape over the outer edges of cavities and continue beyond them. Not every filament owes its position to uplift. Some follow paths that lead inward along gentle gradients in the potential, and some sit in places where sloshing has brought low-entropy gas from one side of the core to the other. The network therefore records more than one transport route lift. Along buoyant channels drift along stratified flows, and quiet settling along shallow slopes in the combined gravitational field. These routes can operate together, and their superposition produces the braided appearance of the core. Uncertainties remain in the microphysics at filament boundaries. The exact rate at which heat enters from the hot phase depends on the degree of field line tangling and on small plasma instabilities that are not directly observed. The fraction of support from cosmic rays is likewise constrained only indirectly. Even with these uncertainties, the persistence, alignment and pressure balance of the lanes are robust. They tell that cold structures can survive for long times, inside a hot sea when fields channel transport and when motion is slow. The network changes the immediate environment. By presenting large radiating surfaces, it allows the core to lose energy, where the hot phase touches the filaments, and by carrying cold gas along ordered paths, it establishes reservoirs that can later feed smaller regions. At this radius, the description stops short of what those reservoirs do inside the central galaxy. It remains with the lanes themselves, which hold their place and shape, while the hot atmosphere flows around them. Ironies stay quiet. It only took the hottest environment in a galaxy system to preserve the thinnest cold threads, because fields and pressure support make what seems fragile endure. Only took slow motion to let structures that stretch for many thousands of light years resist tearing. Only took surfaces a few times thicker than their skins to cool a portion of the core steadily without broad collapse. The filaments and small clouds illustrate the state of the core in a direct way. The atmosphere has enough time and the right gradients to condense. Transport is limited enough to let contrasts live. Motion is gentle enough to arrange structures rather than destroy them. The network is both a product and a tool of cooling it forms because heat is lost, and once present it helps heat be lost where it meets the hot sea. Holding at this scale, the view rests on the picture of long dusty lanes, warm skins and cold cores moving slowly through a hot background. Gravity sets their paths, magnetic fields shape their edges, and pressure maintains their balance. The cluster keeps this layered geometry for spans long enough that the threads can be traced, and their roles in the core's energy cycle can be read without hurry. A single galaxy fills the centre like a low luminous hill whose slopes fade into the surrounding sea. Its light is smooth and extended, brighter than any neighbour, and it stretches so far that the edge is less a line than a long easing into the intra-cluster glow. This is the brightest cluster galaxy. Its stars are old in the main, their colours leaning to red, their orbits arranged into a rounded form that looks simple at a distance, and reveals quiet structure when traced closely. Isophote's contours of equal brightness remain nearly elliptical over great spans, then soften outward into an envelope that blurs into intra-cluster light. The profile rises steeply toward the centre and declines over hundreds of thousands of light years, a continuous fabric of starlight that sits within the cluster's deep well and shares its symmetry. The galaxy does not sit in emptiness. The hot atmosphere surrounds it and flows past at low speeds on these scales. The starlight shines through that atmosphere and through the web of filaments that cross the core. Against the glow, narrow dust lanes mark where cold material has gathered. These lanes draw fine dark strokes over the inner light and bend along the same paths that the cooler gas follows. The dust is thin and localized, and the galaxy's broad light remains smooth beneath it, but those strokes are enough to show that the stellar body, and the multi-phase medium share the same central space. Kinematics add a second view of the shape that light suggests. Absorption lines in the integrated spectrum broaden to widths that reflect the speeds of stars moving in the combined gravity of the galaxy and the inner cluster. Toward the center line of sight, dispersions reach values typical for very massive systems. Rotation is present, but not large enough to dominate the form. Most support comes from random motions in 3 dimensions rather than from spin. The pattern agrees with the round isophotes, and with the expectation for a central galaxy that has grown through many additions over long time. The stars themselves carry a record of that growth. Their chemical abundances read from ratios of elements in the absorption spectrum show enrichment by old generations. Gradients in those ratios indicate that the inner regions hold slightly higher metallicity than the outer. The trend is gentle and typical for a galaxy that has built a dense core earlier and added stars at larger radii later through mergers that were not violent enough to erase the gradient entirely. The Phoenix Cluster's central galaxy follows this family of traits: strong central light, a broad envelope, high central dispersions, and modest rotation. The envelope blends into intra-cluster light that is hard to assign to any one galaxy. This diffuse component is made of stars that drift freely in the cluster potential after being removed from smaller systems by tides or by gentle encounters. It extends well beyond the half-light radius of the central galaxy and contributes a faint pedestal of brightness on which the galaxy's own profile rests. Separating the envelope from the intracluster light is a practical choice rather than a physical break. The stars move in the same field, and the division is drawn by measuring how the profile curves. The shared glow confirms that the galaxy and the cluster are not separate structures laid on top of each other, but one continuous arrangement of stars, gases, and dark matter, with the galaxy's highest densities at the centre. The stellar body interacts with the surrounding medium without strong disturbance. Ram pressure from the hot atmosphere is not enough to reshape the galaxy's deep potential, or to strip stars and the galaxy's motion. With respect to the gas is small at the bottom of the well. Instead, the exchange is by light and by gravity. Starlight illuminates dust lanes that enter along filament paths. Gravity guides both stars and cooled clouds along the same potential gradients. Where lanes cross the galaxy's face, narrow reddish streaks appear against the otherwise even glow. The streaks do not dominate the image, but they are clear, and they align with the gas network rather than with any internal spiral pattern. This alignment shows that the central stellar system is not a disk with strong arms. It is an extended spheroid in which colder structures ride through. The central light profile bends inward without a sharp cusp. In some galaxies, scouring by a past black hole pair can carve a small core with lower central stellar density. In others, continued central star formation can fill a cusp. Here the innermost slope is measured by careful modelling to subtract the bright background and any central point-like light, leaving the star's contribution. The result is a gentle inward rise consistent with many massive brightest cluster galaxies. The exact few parsecs remain challenging to isolate because other components share the same sightline at small radii. But the broad picture is stable. The central galaxy stars build a rounded summit without a sharp spike. Substructure exists but stays quiet. Faint shells and ripples, signatures of past minor accretions, appear as slight departures from smooth contours at large radii when images are stretched to deep levels. Their presence implies that small systems have joined the central galaxy in the recent past by cluster standards adding stars to the envelope. The features are low in contrast and wide in arc, consistent with events that were gentle on the overall form. The galaxy's colour field is similarly placid, a broad redness with slight blueward shifts, where dust lanes allow less reddened light from behind to pass through gaps, and where intermediate temperature gas adds faint emission. These shifts are local, and do not change the main impression of an old population spread over a wide space. The galaxy's mass in stars is high, and its influence on the local potential is strongest within the central few tens of thousands of light years. Outside that, the dark matter halo of the cluster dominates. Within that, the galaxy's gravity adds to the clusters to shape orbits and to deepen the well felt by cold and warm structures. This addition is visible in the way stellar dispersions remain high near the centre, and in the way pressure and entropy profiles of the gas bend inward. The two components share the same centre of mass within measurement limits at the present epoch, indicating that the galaxy has come to rest at the bottom of the well after earlier motions have damped. A lesser-known detail lies in the relation between the galaxy's photometric axis and the orientations of nearby features in the hot atmosphere. In some clusters, the major axis of the central light aligns with the preferred direction of transport in the gas, an echo of the long-term feeding along filaments. In the Phoenix cluster, the inner isophotes and the lanes of cooler gas both favour similar position angles, over tens of thousands of light-years, a quiet sign that the shapes share a history set by the same large-scale geometry. The match is not exact, and it changes with radius as expected when the galaxy's form and the gas network respond to the same field, but on different timescales. The inner regions of the galaxy host compact stellar systems as well. Star clusters populate the halo in great numbers more densely than in less massive galaxies. Their spatial distribution follows the galaxy's profile in the inner parts and broadens into the intracluster population at large radii. Their colours split into families that trace older, metal-poor and somewhat more enriched groups, a pattern common in massive spheroids. These clusters act as traces of the potential and as fossils of past assembly, but do not affect the dynamics at the scales considered here. Remaining at the galaxy scale, the view holds to starlight against gas to shape against medium. The central galaxy is not a brief flare. It is a long-built structure embedded in a longer-lived sea. Its light defines the visual centre of the cluster. Its mass focuses the local field. Its smooth body provides the background against which lanes, dust and faint emission are read. No internal bar or grand spiral breaks the symmetry. No strong disturbance mars the outer envelope. The system presents a calm face that belies the complex exchange of material taking place within and around it. The description stops here inside the galaxy's light, but short of processes that alter its youngest stars or its nuclear engine. The aim is to set the frame a deep, rounded, stellar hill, a smooth envelope joining an even fainter sea, narrow dust marks drawn over the inner glow, high dispersions and weak rotation confirming mass and shape, subtle ripples that record quiet additions, and an alignment between stellar form and the paths along which the surrounding medium flows. The galaxy remains the largest single stellar structure in the cluster and the anchor of the core. Its presence defines place and scale for everything that happens nearer the centre. Inside, the stellar hill signs of recent star formation appear as a faint blue wash, spread across the inner tens of thousands of light-years, and as compact knots sprinkled along the paths of cooler gas. The cooled material that threads the core does not remain only in filaments. Part of it turns into new stars. The light from these stars is young in character, strong in the near ultraviolet, bright in hydrogen recombination lines, and accompanied by dust that absorbs some of the energy and re-emits it in the infrared. The rates implied by these traces after careful correction for dust reach hundreds of solar masses formed each year in the central regions. The Phoenix cluster's core is therefore not only cooling, it is building stars at a level that stands among the highest measured for brightest cluster galaxies. The spatial pattern is broad rather than point-like. Long lanes of cold gas carry star-forming knots outward from the centre, and diffuse young light fills the space between some of those lanes. The clumps are not randomly placed. They lie where cold columns intersect denser parts of the warm network, and where pressure from the hot atmosphere is high enough to compress gas without tearing it. They are most common within a few tens of thousands of light-years of the centre, and thin out beyond that in step with the decline of cold gas along the lanes. The surface brightness is uneven at small scales, but forms a continuous component at larger scales when maps are smoothed. In this sense, the star formation is both clumpy and extended. Ages can be read from colour and from spectral features. The youngest clusters show blue continua and strong hydrogen lines that indicate ages of only a few million to a few tens of millions of years. Slightly older populations add a broader, fainter blue light with weaker lines, placing them within a few 100 million years. The mix says that star formation has persisted over several cycles, rather than occurring in a single short burst. The presence of dust reddening in some knots and heavy extinction toward others means that optical estimates undercount the true rate, unless infrared emission is included. When ultraviolet, optical and infrared are combined, the inferred total restores the hidden share and returns the high values that define the core. The gas that feeds these new stars is the same multi-phase material seen along the filaments. Carbon monoxide maps show cold reservoirs in the central few tens of thousands of light years with masses large enough to supply the observed rates for extended periods if replenished. Kinematics of this gas measured from line widths are moderate, and dispersion dominated with only small rotation signatures. The motions indicate that clouds move in the deep potential rather than in a settled, thin disk. Where they pass near young clusters, the relationship between gas and stars looks immediate narrow dusty streaks, cross bright blue clumps, and emission lines from warm skins surround both, consistent with ongoing conversion from cloud to cluster. Star formation efficiencies on the smallest resolve scales vary across the core. Some knots convert a noticeable fraction of nearby gas within the ages implied by their spectra. Others remain gas-rich with fewer younger stellar points. The differences track local environment. Compression near the rims of buoyant cavities and at intersections of filaments favours higher efficiencies. Quiet stretches along lanes favour lower ones. The average across the star-forming region remains high for a brightest cluster galaxy, but does not reach the extreme densities seen in compact nuclear starbursts of isolated galaxies. The process is distributed, not concentrated, into a single tiny nucleus. Dust plays a double role. It marks cold lanes in silhouette against starlight and hides part of the youngest population from optical view. Infrared maps reveal warm dust heated by young stars and by the diffuse radiation field of the central galaxy. The infrared spectral shape carries signatures of grains and molecules in emission features that confirm widespread recent star formation, rather than aging hot dust alone. When this re-radiated light is added to the ultraviolet and optical, the balance among bands becomes consistent with a long-lived vigorous star-forming episode sustained by the cooling core. The atmospheric context sets the pace. Pressure from the hot medium confines clouds and helps them resist the dispersing effects of young stellar winds. At the same time, the same pressure and heat flow from the surroundings limit runaway collapse by warming cloud surfaces and by keeping filaments narrow and supported. Supernovae from recent generations deposit energy locally, stir gas on small scales, and seed surrounding layers with fresh heavy elements, but their influence remains local compared with the weight of the cluster atmosphere. The net effect is steady building of stars in many places at once, with feedback that shapes cloud edges without unbinding the region. The most luminous star-forming clumps cluster within a few thousand light-years of the very centre, but they do not all sit on the nucleus. Some align along arcs that follow the inner edges of cavities inflated by the central active nucleus, and along the sides of channels where low-entropy gas has been lifted. This alignment supports a picture in which uplift brings cold material to altitudes where it can fragment and form stars, while nearby pressure maintains the conditions for collapse. Other clumps trace gentle rings or partial rings where gas streams orbit before settling a signature of the potential's shape, rather than a separate driver. Uncertainties remain and are noted. The exact stellar initial mass function in these conditions is assumed to follow well-studied forms from nearby galaxies, but direct tests are limited by distance and by dust. Age estimates depend on models that combine star formation history's extinction and metallicity, and they carry ranges that widen where extinction is heavy. Separating light from young stars and light from the active nucleus requires careful modelling that subtracts point-like components and leaves only extended emission. Even with these care points, the picture of high sustained star formation in the extended core remains secure across multiple bands and instruments. Chemical signatures from the hot atmosphere connect to the young stars. High central iron and strong alpha element plateaus shorten cooling times and promote condensation. Those same elements appear in gas phase lines near the star-forming knots, and later in the stellar absorption features of the growing population. The path from enriched hot phase to enriched young stars is therefore visible not only inferred. Over time, this recycling elevates the metallicity of stars formed in the core and helps match the high central metallicities measured in old populations of massive galaxies. Kinematics of the young population agree with the environment. Stellar absorption lines in diffuse blue light show broadened profiles consistent with dispersion-dominated support. There is no thin, rapidly spinning disk that would mark an isolated secular evolution. Instead, stars inherit the velocities of their parent clouds, which are set by the deep potential and by gentle flows that curl around the centre. As they age, these stars blend into the broader, redder population and add to the mass of the central galaxy without changing its basic rounded form. A lesser-known detail rests in the relationship between star formation and the soft intermediate temperature layers on filament surfaces. These layers radiate strongly and can cool further where surface pressure is high and where heat inflow is modest. In places where two surfaces meet, or where a surface encounters a mild shock from a passing wave, condensation can proceed quickly to the cold state, and star formation begins at the junction. The geometry of the network therefore seeds star-forming sites by increasing interface area and by creating mild convergences without requiring strong external triggers. The core's high rate does not imply that all cooled gas becomes stars. Measurements of molecular reservoirs indicate that a large mass remains in clouds, even as clusters of young stars appear. The balance between gas turned into stars and gas left for future cycles varies with radius and with time, but a common finding is that only a portion of the potential cooling flow reaches the stellar phase. The rest stays in the cold or warm state, returns to the hot medium by mixing or gentle reheating, or feeds the small region at the nucleus. The fraction that reaches stars is however large enough to grow the central galaxy measurably on timescales short compared with the age of the cluster. The view holds at this region and does not step inward to the nucleus. It remains with the extended star-forming core diffuse blue light that covers much of the inner tens of thousands of light years. Compact clusters spaced along cold lanes and around cavity rims, dust lanes that both reveal and conceal, infrared glow that restores the hidden share, and rates that after correction reach hundreds of solar masses per year sustained over long intervals. The process is organised by gravity and pressure, moderated by conduction and gentle turbulence, and supplied by the same multi-phase atmosphere whose paths have already been traced. The central galaxy, seen earlier as a calm, rounded hill of old stars, now carries a layer of recent work upon it, bright enough to measure, yet quiet enough to preserve the broad form beneath. At the very centre, a compact engine works in quiet cycles. A black hole of great mass sits within a small region, and draws in part of the cold and warm material that settles near it. As gas approaches, gravitational energy turns into heat and radiation. At the same time, some of that energy leaves along narrow channels as jets. These jets are collimated flows of relativistic particles and magnetic fields that drill through the inner atmosphere and then slow widen and rise. They do not carve tunnels in the usual sense. They inflate light, high-energy lobes that displace the denser hot plasma. In X-rays, the displaced regions appear as cavities, dim rounded depressions next to the nucleus. In radio maps, the same regions shine filled with synchrotron emission from electrons spiraling in magnetic fields. Together, these pictures show that the engine couples to the surrounding gas mechanically not only with light. The cavities are not empty. They contain relativistic plasma that weighs less than the displaced hot gas. Buoyancy lifts them away from the centre once the jets have supplied enough pressure. As they rise, they do work on the atmosphere, pushing aside denser layers and leaving rims where gas has been compressed. In some places, weak shocks form around the youngest cavities. These shocks are gentle with small increases in temperature and pressure, but they travel and carry energy outward. Farther from the origin, the shocks fade into sound waves, broad low contrast ripples that move through the stratified medium and dissipate slowly. The sum of this work, jet thrust cavity inflation weak shocks, and sound spreads the engine's power over the core without relying on one violent event. The energy scale is read from the cavities themselves. Their volumes are measured from maps. Their internal pressure is taken to match the pressure of the surrounding gas that confines them. The product of pressure and volume gives a baseline energy for inflation. Accounting for the rise and for the work done on the atmosphere increases that estimate by a modest factor. Dividing by the time since inflation began yields a power. In the Phoenix cluster and other strong cool cores, these powers are large enough to offset most of the radiative losses in the inner tens of thousands of light years. The conclusion is cautious but steady. Mechanical feedback balances cooling to first order with variations in time that the atmosphere integrates. The engine does not run at a single setting. Jets brighten and fade. Cavity sizes and positions change with each cycle. Sometimes a pair is nearly north-south, and the next stands at a slight angle. Precession changes in accretion rate and modest asymmetries in the medium all contribute to this variety. Yet the broad pattern repeats young cavities near the centre, older ones higher up, rims that trace compressed gas, faint ripples that curve away in nested arcs. The Phoenix cluster shows this sequence clearly. Multiple generations of cavities align roughly with one another, but not perfectly a sign that the engine and the atmosphere negotiate their terms over many tens of millions of years. The interaction lifts more than volume. It carries metals. As bubbles rise, they drag a thin skin of surrounding gas along their flanks. That gas is often enriched by past star formation in the central galaxy. The lift carries it to larger radii where it mixes laterally and leaves ridges of higher abundance aligned with radio channels. The same motion stretches cold filaments into arcs that drape over cavity rims as already noted. In this way, feedback redistributes both heat and composition, raising entropy mildly, where rims pass and spreading heavy elements along preferred paths. Not all heating is in waves and shocks. Viscous dissipation of small motions, turbulent mixing at cavity edges, and scattering of sound into heat contribute steadily. The rates depend on the effective viscosity and on the microphysics of the plasma. Observations that compare the total radiative losses to cavity power argue that these channels together are sufficient when averaged over time. Where the atmosphere shows broad ripples and gentle pressure gradients, the distribution of energy appears smooth rather than patchy. A lesser-known detail sits in the role of cosmic rays within the cavities. The lightness of the bubbles implies support from non-thermal components. Cosmic ray pressure and magnetic fields both contribute. If a small fraction of those particles leak or stream into the surrounding gas, they can transfer heat through wave damping. Whether this process is significant varies with field geometry and with the spectrum of particles. Measurements of gamma rays from clusters place limits on the hadronic component, suggesting that most support is leptonic and magnetic. Even so, the possibility that streaming adds gentle heating in thin boundary layers remains open within allowed ranges. The engine's duty cycle is written into the spacing of cavities and ripples. New pairs appear on timescales of tens of millions of years, consistent with the time required for a bubble to rise, a distance comparable to its size, and for accretion to rebuild pressure at the centre. This rhythm matches the cooling clock in the same region, within an order of magnitude, a natural condition for self-regulation. When cooling supplies more low-entropy gas, accretion strengthens, power rises, and heating spreads. When cooling ebbs, accretion softens, power falls, and the atmosphere drifts inward again. The balance is not perfect at every moment. It is close enough that large departures do not persist. Uncertainties are plain. The exact accretion mode, cold clouds sinking from filaments hot gas captured from the atmosphere, or a mix varies with time and remains difficult to apportion. The conversion from inflow to jet power depends on magnetic flux near the black hole and on spin parameters that cannot be measured directly here. The partition of mechanical power among cavities shocks, waves, and mixing changes from cycle to cycle. Even with these unknowns, the observational ledger closes within comfortable errors. Mechanical output inferred from cavities matches, radiative losses from cooling gas over broad intervals. The surrounding medium answers rather than yields. Magnetic draping along cavity surfaces limits mixing and helps maintain their shape. Vorticity shed from rising bubbles seed turbulence that decays slowly and helps spread energy in 3 dimensions. Where shocks cross cold fronts, some edges sharpen and others soften depending on the angle and on the local field. The atmosphere records each passage in subtle changes of brightness and temperature that require long exposures to see. The engine's light carries fewer clues than its work. Point-like emission from the nucleus varies, but the most reliable evidence of energy transfer remains mechanical. This is practical. Radiation can escape without heating the gas. Mechanical power must interact to make room for itself, and that interaction is the very feature that reveals it. Thus, the cavities become the central measure, the ripples, the confirming signature, and the alignment with radio structures the identification tag. Feedback does not erase cooling. It moderates it. The core remains multi-phase. Filaments persist. Star formation continues at rates high for a central galaxy. What changes is the pace without feedback. The notional cooling flow implied by profiles would be larger by factors of several to many. With feedback, the flow is shared among star formation molecular reservoirs, gentle return to the hot phase through mixing, and a smaller share into the engine itself. The atmosphere holds near a steady floor of entropy, rather than sliding to zero. A lesser-known detail lies in the faint older cavities that drift to radii, where buoyancy slows their rise, and where they disperse into the background as ghost bubbles. Their rims fade, their radio emission ages and dims, yet their displacement remains as a memory in the pressure field. Counting these ghosts expands the energy budget beyond what the bright young cavities alone would imply. In the Phoenix cluster, the number and size of such features support a long history of repeated outbursts. Remaining strictly at this scale, the description ends with the pattern itself. A compact engine draws fuel and returns power. Jets inflate bubbles. Bubbles rise, push, and lift. Weak shocks and sound carry energy outward. Rims compress gas and mark paths. Metals are redistributed along channels. Filaments drape and survive. The core's cooling is opposed not by a single event, but by many small ordered actions that spread heat without breaking the structure. The balance is imperfect in detail and durable in sum. The cluster keeps this exchange for spans long compared with human life, and short compared with the age of the system, and in that interval the inner atmosphere remains bright layered and held. Within the central few tens of thousands of light years, cooled material gathers into reservoirs whose mass rivals the gas bound in many entire galaxies. These reservoirs are not single pools, they are collections of clouds and streams mostly molecular, interlaced with warmer skins and embedded dust. Their presence is measured by lines from common molecules such as carbon monoxide, and by far infrared emission from dust grains warmed by nearby stars. Maps show that the densest gas concentrates within a few tens of thousands of light years of the centre, and that its surface brightness follows the network of filaments already traced. The total mass implied by these traces reaches values large enough to sustain the observed star formation for many tens of millions of years even without fresh supply. The gas is not arranged as a thin rotating disk. Kinematic maps reveal dispersions that are high, compared with any ordered spin and velocity gradients change direction from place to place. Some regions show slow rotation on kiloparsec scales, others show counterflows and bends that mark intersecting lanes. The motions are consistent with clouds moving in a deep potential aided and hindered by pressure from the hot atmosphere and by magnetic tension along their paths. Where clouds gather, they do so in clumps and short streams rather than in a single ring. The result is a reservoir that fills volume, not just a plane. Gravity guides the large-scale path inward. Pressure from the hot medium resists the smallest fragments, preventing free fall and spreading momentum between phases. Magnetic fields help keep clouds coherent by limiting shear and confining charged particles to narrow paths. In this combination, clouds drift, collide, softly merge, and sometimes break apart. Their lifetimes are not set by a single clock. Cooling conduction, mixing star formation, and gentle stirring all act at once. Observations show clouds that are bright in molecular lines but faint in star formation, lying alongside others where young clusters already shine. This diversity says that the reservoir is both supply and product, at the same time reworked continually by local conditions. The exchange with the hot atmosphere is steady. Interfaces at the cloud surfaces radiate strongly, allowing energy to leave the core without requiring that every parcel reach the coldest temperatures. Some mass returns to the hot phase through mixing layers and slow evaporation. Some mass remains cold and drifts inward. Some is converted into stars, and some, a smaller portion, moves along channels that approach the nucleus. The proportions change with radius and with time, but the presence of all four paths is a stable feature of the core. A lesser-known detail sits in the cloud-size spectrum. Interferometric maps resolve structures from hundreds down to tens of light-years across, and find no single preferred scale. Instead, clouds and clumps appear in a hierarchy. Large complexes break into knots. Knots hold smaller cores. This hierarchy allows a wide surface area for exchange with the hot phase, and increases the effectiveness of radiative cooling at the boundaries. It also means that angular momentum can be redistributed by many small collisions and near misses, rather than by one dominant torque. The path inward is therefore neither smooth nor blocked. It is incremental. Pressure confines the reservoir, but pressure also assists its redistribution. In regions near cavity rims or along weak shock fronts, compression raises density in parts of the network and shortens local cooling times. Their clouds can grow mass by condensing mixed gas from their skins. In quieter regions, conduction from the hot medium warms outer layers and slows condensation. The balance shifts from place to place, producing patches where mass accumulates and patches where it thins. Over long intervals, the net effect maintains a large cold mass near the centre, while allowing steady leakage inward and outward. The outward path is not a wind in the usual sense. Cold gas rises only when it is entrained by buoyant bubbles, or carried by broader sloshing motions. Lifted parcels often arch over cavity rims and stall at radii where buoyancy and gravity balance. There they can linger fragment and rain back along curved paths. This return flow leaves loops and partial rings of molecular emission that match the geometry of older radio structures. The Phoenix cluster shows such loops with velocities that first rise away from systemic near the nucleus, then ease toward it at larger radii as clouds turn and descend. These patterns support the broader picture of circulation rather than one-way transport. The inward path shows corresponding signs. Clouds farther out carry higher specific angular momentum on average. As they drift inward and collide, their directions scatter and their net spin declines. Where gentle shear or compression brings two lanes together, clouds can lose angular momentum by sharing it, allowing a fraction of their mass to sink deeper, while another fraction is deflected outward or sideways. In this way, the reservoir feeds the inner radii without forming a thin disk at once. The process is not efficient in the short term, but is persistent, and persistence is the relevant measure at cluster timescales. Uncertainties remain in how much support cosmic rays provide inside the cold phase, and in how much magnetic tension resists cloud shredding. Limits from gamma-ray observations argue that cosmic ray pressure is not dominant across the volume, yet localized contributions may be important where fields are strong and tangled. Likewise, the degree of turbulence inside the reservoirs is measured indirectly by line widths, and carries ranges that include both genuinely turbulent motions and the superposition of many narrow streams in the beam. Even with these ranges, the conclusion that the reservoir is dispersion-dominated and three-dimensional, rather than a single rotating sheet, holds. The reservoir's chemistry reflects its origin and its processing. Gas phase metallicities near and above solar values measured from line ratios in the warm skins and inferred for molecular cores match the enriched hot atmosphere and the central stellar population. Dust-to-gas ratios are lower than in the disks of normal star-forming galaxies, but high enough to shield molecules and to seed cooling in the cores. Where shocks at a few tens of kilometers per second pass through lanes, molecules like hydrogen can be excited without dissociating, adding to the infrared glow without destroying the cold phase. These shocks are not strong enough to disperse the reservoir. They mark places where pressure has changed recently, often near cavity edges or along returning flows. The mass budget closes within comfortable limits when all phases are counted. X-rays measure the radiative losses of the hot phase. Infrared and ultraviolet light measure star formation in the cold phase. Molecular lines measure the reservoir mass available for future stars and for drift toward the nucleus. Cavity energetics measure mechanical input from the center. Over intervals of tens of millions of years, the power from cavities balances most of the X-ray loss, keeping the hot phase from collapsing in bulk. The remaining share of cooling is expressed in the growth of the reservoirs and their conversion into stars, with a smaller fraction reaching the very center as fuel. In this partition, the reservoir acts as a buffer that smooths variations in supply and demand when cooling outpaces heating. Briefly, cold mass grows. When heating runs ahead, mixing returns some of that mass to warmer phases. A lesser-known detail lies in the correlation between the spatial extent of the reservoir and the region where the cooling time to freefall time ratio falls to values of order 10. In maps that place these quantities together, the outer edge of widespread molecular emission roughly matches the contour where this ratio first dips below that threshold. The match is not exact at every angle as expected when motion and field geometry matter, but the broad agreement supports the idea that thermodynamic conditions set the stage for where gas can condense and persist. The return flow shapes stellar histories. Clouds that rain inward along curved paths pass through zones where pressure and shear differ. In some zones they fragment and form stars. In others they remain intact and drift on. Young clusters left behind record the passage as faint arcs of blue light that trail the current positions of the densest gas. Over time, these trails fill the inner galaxy with a diffuse young component, while the main body of the reservoir continues to feed later stages. The description remains at this scale, and does not cross into the final approach to the black hole. It holds with the cold mass and its motion, a large turbulent three-dimensional reservoir. Clouds and streams that collide softly and trade angular momentum, uplift and rain that complete broad loops, compression near rims that gathers mass, conduction and mixing that return some share to warmer phases, and steady extended star formation that draws from the same supply. The reservoir's role is structural. It stores what the atmosphere condenses, moderates how that condensation appears, and meters the delivery of material both to widespread star formation and to the innermost regions. The core keeps this circulation without drama. Rates change slowly, paths shift with each new bubble, and the net balance holds for long periods. The cluster center is thus neither a sink that swallows all cooled gas at once, nor a fountain that ejects it to the outskirts for good. It is a basin with inner eddies fed by the same multi-phase atmosphere already mapped and organised by gravity pressure, and fields into a long-lived store that supplies the next smaller scale. At the smallest radii, the flow becomes a different kind of weather. Clouds that have drifted and traded momentum in the reservoir gather within a few hundred light-years of the centre, and meet a region where gravity steepens quickly. Here, motions that were dispersion-dominated become organised enough to feed an accretion flow. The accepted picture at this scale is simple and sufficient. Some fraction of the cold and warm material loses enough angular momentum to cross inward, while the surrounding hot atmosphere also contributes a slower drift. Together they assemble a compact rotating structure whose inner parts deliver gas to the black hole, and whose magnetic fields and pressure gradients lift energy away. The light from stars fades against the point-like nucleus. Gas becomes the main actor. The flow is not a single thin disk as taught in early sketches. It is a layered arrangement. At the outer edge of this zone, tens to hundreds of light years across cold clouds and warm skins still appear as clumps and short streams, although their paths now arc around the centre with clear ascents. Collisions among these clumps, assisted by tidal forces in the steep potential, shed angular momentum and allow a portion of the mass to settle into a thicker, more continuous ring. In this ring the gas remains clumpy, yet rotates as a whole, supported partly by spin and partly by internal pressure. Closer still, within only a few light years, rotation takes a larger share of the support. Temperatures rise as shocks thermalize orbital shear, and as radiation from the innermost flow warms the layers above and below the midplane. Magnetic fields tightened by rotation begin to matter more than geometry for how momentum moves inward. The result is a compact magnetized flow that can supply the innermost engine. The inflow time is shorter here than anywhere outside, but it is still long compared with a human span. The supply therefore averages over many small changes. Some days deliver more low-entropy gas from a filament intersection, some deliver less. The flow absorbs these variations and passes only a smoothed version to the black hole. This smoothing is one reason the cavity power and the core's cooling rate can remain in broad balance. The fuel line does not turn on and off sharply. It narrows and widens within limits set by gravity and by the angular momentum budget. The line of demarcation between cold-fed and hot-fed accretion is not a rigid distance. Where clouds reach inward alive, they can feed the inner flow as distinct parcels. Where they are warmed or shredded by mixing and radiation, their mass joins a hotter, thicker layer that trickles inward more slowly. Both routes likely operate together. The relative share varies with time and with how much cold mass reaches the circumnuclear ring. A lesser-known detail lies in the way small gravitational torques arise, even when no large bar or spiral exists. In a thick, clumpy ring, uneven densities and self-gravity create transient non-circular structures, short arcs, weak lopsidedness that tug on neighbouring gas, and move angular momentum outward in exchange for inward drift. This internal stirring works alongside magnetic stresses that act within the more continuous inner layers. Neither process produces a grand pattern on the sky, yet both are effective because the potential is steep and the dynamical time is short. The innermost region, smaller than a light year across, cannot be resolved in a cluster this distant, but the physics that operates there is steady in outline. Gas orbits many times per year at those radii. Magnetic fields wound by rotation drive turbulence that moves angular momentum outward and mass inward. The rate of inward drift adjusts to the pressure set by what the outer ring supplies, and by how much energy is carried away. If magnetic flux piles up near the black hole, the inner flow can enter a state in which fields dominate the dynamics close to the horizon. In this regime, the same fields that move momentum outward through the disk also launch energy upward and downward along the rotation axis. The outflow emerges as tightly collimated jets, already described at larger scales. Here the focus remains on the base, a compact magnetized engine that converts a fraction of gravitational energy into directed power while allowing the rest to heat and light the immediate surroundings. Radiation from the inner flow does not escape freely into empty space. It crosses gas and dust in the circumnuclear region and is partly absorbed and re-emitted in the infrared. It also changes the temperature of the upper layers of the ring, tending to puff them and to slow the direct fall of new clouds by raising the pressure they must push against. This radiative feedback is gentler than the mechanical work of jets at cluster scales, but is decisive close in where every small change in pressure can move or stall a parcel. The balance between radiation, magnetic stress and gravity determines whether the flow stays thick and relatively dim, or thins and brightens for a while. In the Phoenix cluster's core, where mechanical feedback dominates the energy ledger at larger radii, the inner flow often remains in a mode where much of the power leaves as mechanical work rather than as light. Uncertainties remain where they should. The exact partition between cold parcels that survive to very small radii and hot gas that trickles in from the atmosphere is not measured directly. The geometry and strength of magnetic fields at the last stable orbits are inferred from models and from analogues nearer by not mapped here. The spin of the black hole, which affects how efficiently fields can tap rotation to launch jets, is not known for this system. Even so, the larger behaviour sustained mechanical output, repeated cavity inflation, and a core that stays multi-phase constrains the inner solution to a set of possibilities that all include a magnetised rotating engine fed by a mix of clumps and warm gas. The circumnuclear ring is not inert. Stars can form in its densest pockets where shear is gentle enough and where radiation does not evaporate small cores. Young clusters observed within a few thousand light-years of the nucleus testify that this happens intermittently. Their masses remain modest compared with the inflow budget, so they trim rather than block the supply. Supernovae from these stars stir the ring and add metals to the local gas, which shortens cooling times in the surface layers. The net effect is to roughen the inflow rather than to end it. Dust mixed into the ring also evolves. Grains grow in cold pockets and are destroyed by sputtering where shocks and radiation heat them. The balance shifts on scales of years to centuries at the smallest radii far faster than the outer reservoir changes. Those changes imprint only as small modulations on the infrared glow seen in larger apertures. A gentle mystery remains in the exact handoff from the clumpy ring to the continuous inner flow. Observations in nearer systems show streamers that break and reconnect, brief, circular flows that stall and then resume, and low-level winds from the surface that return part of the mass to slightly larger radii. How these features scale in a cluster core where pressure and gravity are both extreme is still being explored. The Phoenix cluster likely participates in the same family, with a balance that favours feeding the engine enough to power jets, while keeping part of the inflow bound in the ring. The inner layers communicate outward. Alphenic and acoustic disturbances launched near the black hole travel through the ring and into the surrounding atmosphere, arriving later as the faint ripples mapped in X-rays. These waves carry only a small share of the engine's power at any moment, but they add coherence to the feedback by smoothing hot gas on scales much larger than the ring itself. In this way, the sublight-year region and the tens of thousands of light-years region stay linked by weak signals that the stratified atmosphere can carry without tearing. A lesser-known detail is the slow precession that small tilts can induce. If the inner flow's angular momentum is misaligned by a few degrees with the outer ring, or with the black hole's spin frame dragging effects and internal torques, can twist the inner flow over times of thousands to millions of years. The result is a gradual change in jet direction that, when integrated over many cycles, produces families of cavities at slightly different angles. The Phoenix cluster shows such families. Their geometry allows a quiet inference that the inner flow has not held a single orientation throughout its history. The accretion rate that reaches the horizon is smaller than the total mass dropped out of the hot phase. Most cooled gas either becomes part of the molecular reservoir or is returned to warmer phases by mixing and gentle heating. The share that does reach the black hole while small in mass is still ample in energy, because the conversion from mass to mechanical work is efficient in a magnetised rotating system. This asymmetry is central to how the core holds steady. A little fuel properly arranged suffices to inflate cavities, whose combined work balances a much larger mass of gas that would otherwise cool unchecked. Remaining strictly at this region, the description ends where inflow touches the engine. Outside, clumps and streams enter a ring that is thick, slowly rotating and magnetised. Inside, rotation wins fields, magnetic stress moves momentum outward, and a compact flow feeds the black hole while launching power along the axis. Radiation from the inner flow warms the nearby layers. Mechanical energy rises as jets. Weak waves spread the news through the core. The pieces do not need to be seen directly to be known in outline, because their effects propagate outward, as cavities ripples, and the survival of a multi-phase core whose clocks do not run to zero. The smallest region therefore completes the path inward a reservoir that narrows into a ring that hands inward to a compact flow, and a compact flow that closes the loop by sending energy back into the surrounding atmosphere. Each part holds within ranges, changes within ranges, and keeps the larger system within the corridor set by gravity, and by the cooling and heating it permits. The centre and the outskirts keep time together, each in its own register. The outer halo changes slowly with pressures and entropies that shift over spans longer than any single episode near the core. The inner tens of thousands of light years change more quickly, with clocks set by cooling, by buoyant rise, and by the turnover of small waves. The Phoenix cluster holds these tempos at once. The outer sea remains stratified and close to hydrostatic balance. Entropy rises with radius and resists overturning. Weak turbulence decays at a measured pace, adding a small share to support and then fading. The boundary where infall becomes heat stands far out, its shape renewed by steady supply along filaments. Within that boundary, pressure profiles evolve almost imperceptibly, guided by the same dark matter, that ages only by gentle additions at its edge. The inner sea keeps a different calendar. Cooling times shrink inward from spans longer than the history of the cluster to spans that are short on galactic scales. Near the entropy minimum, gas separates into phases. Cold filaments form and survive, warm skins shine, and molecular reservoirs gather volume. Young stars appear along lanes and around rims where pressure is high. Cavities swell and rise, sound waves travel outward and soften, and the next pair of bubbles begins before the last pair has fully dispersed. This cadence is not a single drum, but a set of nested rhythms that align often enough to hold the core steady. One clock is set by radiative loss in the cooling region. The power required to replace that loss is read from X-ray maps and from the abundance of heavy elements that strengthen line emission. Another clock is the buoyant time of a cavity measured from its size and its distance from the nucleus. A third is the interval between ripples, the spacing of faint brightness crests that mark outward-going waves. When these intervals are compared, they sit within an order of magnitude of one another across the inner region. That proximity allows the engine to respond within a useful window, not instantly, not late. A lesser-known detail sits in the wandering phase of these clocks. The time between bubble generations lengthens or shortens as the circumnuclear ring widens or narrows. The mean spacing of ripples responds as the sound speed changes with small temperature shifts. The local cooling time shortens where filaments present larger surfaces and lengthens where a weak shock has recently passed. None of these wanderings breaks the alignment. They move together because each depends on pressure, temperature, and geometry that the others also influence. The cluster uses this mutual dependence to keep departures from balance brief. The hot atmosphere remains the frame that sums these motions. Waves cross large angles with modest dissipation, smoothing small imbalances without erasing gradients. Cold fronts slide and shift metals sideways, spreading the products of stars and altering local cooling with only small changes in pressure. Magnetic draping stabilizes edges and channels heat along field lines, so that transport becomes directional rather than isotropic. These channels allow the core to share information about pressure and temperature over distances greater than any single cavity can reach, and they do so without asking the gas to mix completely. The molecular reservoir acts as a buffer between the hot sea and the innermost engine. When cooling briefly runs ahead of heating, the reservoir grows and the star-forming layer brightens. When heating leads mixing, returns a fraction of the reservoir to warmer phases and star formation eases. The share that reaches the nucleus adjusts over longer cycles set by the inward transfer of angular momentum. This buffer keeps short variations from reaching the engine as shocks, and instead delivers them as a slow drift in supply. The result is a core that moves within bounds, filaments persist, stars continue to form cavities, repeat, and profiles keep their shapes. The outer halo answers these inner cycles in small ways. Weak shocks and sound waves steepen slightly where they cross regions of low entropy and flatten where entropy rises. Abundance ridges mark channels of uplift, and later drift outward by a few tens of thousands of light-years over many cycles. The Sunyaev-Zeldovich signals shift subtly as pressure is redistributed by the gentle work of repeated bubbles. These changes are not dramatic, but they are cumulative, and they write the effects of the inner engine across a volume large enough that the cluster's largest maps can read them. Uncertainties remain where clocks meet physics that must be averaged. The effective viscosity that damps turbulence sits within ranges. The suppression of conduction across tangled fields varies with radius. The spectrum of waves launched by the nucleus is not resolved, and must be inferred from ripple spacing and contrast. The measured totals continue to fit within comfortable limits. Cavity powers for many cycles together equal radiative losses to within typical uncertainties. Star formation rates and molecular masses together account for a substantial share of the residual, and the persistent presence of a multiphase core implies that neither heating nor cooling dominates for long. The galaxies inside the cluster carry their own slower metronomes. Ram pressure trims gas from satellites over orbits that last hundreds of millions of years. Stars in the central galaxy age over billions of years, while new clusters add a young layer near the nucleus. Type Ia supernovae continue on long timescales and lift iron abundance incrementally, while the short-lived massive stars formed in the core contribute alpha elements promptly. These slow and fast channels together maintain the chemical map that cooling now reads. In this way, clocks in the stellar body and clocks in the gas remain linked. A gentle analogy remains within bounds. The cluster is a basin where long swells and small ripples pass through each other without confusion. The swells are the slow change of the halo and the pressure field. The ripples are the repeated bubbles and waves, and the foam at the edges is the fine structure of filaments and young clusters that comes and goes on the shortest times. No single swell or ripple sets the scene, the combination does. The smallest region closes the loop by returning power outward. As jets inflate cavities, as rims compress gas, and as ripples spread, the entropy floor in the core is kept from dropping to zero. The cooling flow that would follow from profiles alone is reduced to a fraction of its notional value. What remains feeds, stars maintains reservoirs and supplies the engine itself. The percentages shift with time, but stay within ranges set by the same conditions that made a multiphase core possible. The duty cycle of the engine is therefore not an external imposition. It is the near result of inner supply of ring and reservoir geometry, and of the response of the stratified sea to small disturbances. The outer halo continues to anchor this activity. The dark matter well holds the atmosphere in place. The shock at the boundary continues to convert in fall into heat. The global pressure profile sets the background against which ripples and fronts move. Because the outer structure changes slowly, the inner cycles repeat against a steady field. This steadiness lets faint features accumulate into clear maps, metal stretched into arcs, cavities traced over generations, and filaments that drape along the same paths again and again. A lesser-known detail sits at the margins of the core, where the ratio of cooling time to freefall time rises through values, where condensation ceases to be common. Their warm emissions, thin molecular lines fade, and X-ray brightness resumes its simple stratified decline. This boundary is not a hard shell. It wavers where uplift has recently carried gas outward, and where small waves have raised or lowered entropy. Even so, it remains recognizable over long periods, and the extent of the reservoir tends to track it. The cluster keeps all these clocks without a single conductor. Gravity sets the beat of orbits and of buoyant rise. Pressure and entropy profiles pace cooling. Magnetic fields and viscosity manage how quickly motions damp. The black hole's engine responds to what the ring supplies. Stars light what cold gas becomes. Nothing here demands a crescendo. The system moves within corridors where extremes are rare and long-lived structures are favoured. The outermost map remains calm while the inner map writes and rewrites its fine script at a measured pace. The section does not step beyond the present radii. It ends with the rhythms in place, an outer halo that holds an inner core that cycles reservoirs that fill and drain within limits, stars that continue to form where pressure is high and cooling is quick, and cavities that rise and spread energy until their rims fade into the same sea that formed them. The Phoenix cluster continues to keep time in layered ways, each register steady enough to be mapped and slow enough to sleep beside. Night settles over instruments and screens. A soft hush fills rooms where charts glow and then dim. Far away, the cluster remains in place, a quiet basin in a wider web. Its hot sea held its inner lanes unhurried. Air cools. Floors keep their steady weight. The world becomes simple again. Breaths take the same measured length. Time loses edges and moves as one even surface. Numbers loosen, slipping back into blankness. Lines on maps become mere lines. Light becomes a calm idea rather than a thing that must be caught. Stars turn behind thin cloud, and the long structure of space keeps its shape without effort. Pressure stays where it has been placed. Entropy holds its slow ladder. Gentle waves cross a distance that is not counted now. Cavities rise somewhere, and then are forgotten by the gas that close behind them. Filaments rest in their narrow paths, supported and still. Nothing asks for a decision. Nothing waits. The cluster exists complete in the way quiet things are complete. In the room, sounds withdraw until they are only a faint hum, and then less than that. The body settles into the furniture of darkness pillow blanket, a small island of warmth. Thoughts arrive farther apart and then do not arrive at all. Breathing remains, gravity remains, a dim awareness of space remains and then smooths into absence. The sky above the roof is unchanged by any of this. It accepts the hour, and the hour becomes simple and slow. A final trace of light lingers behind closed eyes and then passes. Silence takes the last detail and sets it down gently. Rest gathers unbroken as if it had been here all along, waiting with the same patience the cluster keeps. Everything holds. Everything is still.